Today we are starting chapter 15, which is entitled The Electric Field of Distributed Charges, and we'll see in a minute what that actually means. For those of you who've been dying for more math, we're going to have more math here. And the basic idea is that up to now we've looked at the electric field of 1-point charge and 2-point charges, a dipole, and we've seen how electric fields can affect matter. But mostly we don't have single point charges around. We have macroscopic objects that are charged, like pieces of invisible tape or something like that. And so the question is, how can we figure out what kind of an electric field, say, a charged piece of invisible tape would make throughout space? And to do that, we need to use some mathematics and the superposition principle. One of the directions we're going with this is that it's going to become increasingly important to us to understand excuse me, what kinds of patterns of fields in space are possible. You've already seen two that are really different. The field of a point charge just sticks out or in from the point charge. The field of a dipole points in pretty interesting directions, and it's got some sort of curvature to it. And so the question is, what other patterns of field are possible? And it turns out that there are patterns of field that are actually impossible. And so we want to get a sense for what kinds of charge distributions make what kinds of patterns of field, and eventually we're going to codify that in a set of equations that are called Maxwell's equations. Along the way, we want to get some, if we can, distance dependencies. So we saw the field of a point charge fell off like 1 over distance squared. The field of a dipole fell off faster, like 1 over distance cubed. I want to see what other kinds of distance dependencies we might be able to observe. And to do that, we kind of have to get algebraic expressions for the magnitude of the electric field as a function of distance from the source. So that's where we're going in this chapter. Along the way, we will use some calculus. And one of the points that we're going to make is that this integration variable thing that you're used to writing, the dx or dy or something when you have an integral, that's not declaration. That's actually really an essential part of adding up fields. So we're going to be paying special attention to that kind of thing. So let's get started. So let's imagine that we have a fairly simple charge distribution. Let me switch cameras here. Okay. We have, what we've done is we've taken something like maybe even just like a plastic ballpoint pen. In fact, this is a better plastic ballpoint pen because it's actually all plastic. And we've just rubbed it on our sweater. And we find that it's now charged. What do we expect the electric field? And we don't know what's happened. Either electrons got transferred or ions got transferred between the sweater and the pen. We're not quite sure which, but the result is that this pen has a non-zero net charge now. And we want to predict what the electric field is going to look like around the pen. Now, so here's maybe our charged pen. And let's say it's charged positively, even though that's probably not realistic, but it's just easier to deal with algebraically. So suppose we have a uniform positive charge distributed all over the pen, which we indicate like this. And I'm drawing again these little pluses on the surface to indicate that they're charges. I'm drawing them outside the outline of the pen to indicate that they're on the surface. And we want to calculate the electric field somewhere, say here. What would happen if we put our proton on a spring at this location, or at this location, or at that location, what kind of an electric field would we detect there? Well, the problem is that we have a lot of charges on the pen. Okay, there's going to be a lot of excess charge. If, for example, the charge on the pen was approximately a nanocoulomb, that would mean that we have something on the order of, we have 10 to the minus 9 coulombs divided by, let's say we've lost electrons, so this thing, let's make it a glass rod, okay, so we can legitimately be positively charged. So we'll call it a glass rod. It's a stirring rod from chemistry. And so we have a deficiency of electrons, which means we've got some excess protons around. So the charge of a proton was 1.6 times 10 to the minus 19 coulombs per proton. And so that's something on the order, so 1.6 is about 2, so it's something on the order of 0.5 times 10 to the 10th excess positive charges here. So on the order of 1 times 10 to the 10th excess charges. Well, where are they? We don't even know where they are there, but we know they're more or less, we assume they're more or less uniformly distributed over the surface of the pen. So it's going to be really impractical to find, to even guess at the location of 10 to the 10th excess charges, and then try to draw vectors R from there to the observation location and add them up. That would, so what we're going to do is this, and this is sort of the key ploy we use in doing these things. What we're going to do is divide our rod into some number of pieces, and we're going to start out with a finite number of pieces. So let's say we divided it into 4 pieces. And we said, well, we're going to approximate each of these pieces as if it was a point charge. So what we would do is we would treat the rod as if this first piece was a point charge here, and this second piece was a point charge there, and the third piece was a point charge there, and the fourth piece was a point charge there, right? And now we have a small number of point charges, and we can just use the superposition principle. So we can draw our R vectors to our observation location. So that would be R for piece 1. The piece 2 would have a different R, and piece 3 would have a different R, and piece 4 would have a different R. And we could do that for any observation location. So, so this is a very general scheme. So if we wanted a different, this observation location, that would be R1, and that would be R2, and that would be R3, and that would be R4. Okay, so we have a very general sort of approach, and then we just treat those as, so at this observation location, E net would be E1 plus E2 plus E3 plus E4. And in fact, we typically actually are going to write these not as E1, 2, 3, 4, but what we're going to write them as a delta E. So let's move this out of the way. So we're going to write this as delta E sub 1, because it's only a piece of E. It's the piece of E due to segment 1 here. plus delta E sub 2 plus delta E sub 3 plus delta E sub 4. So that's the scheme we're going to be using to add up contributions to electric field to get the net electric field. This is very general. And as you can probably imagine, the more different pieces we divide the rod up into, the more accurate our calculation of field is going to be. Up to some point where then after that, it isn't actually going to matter. You know, we're not going to see much difference. But probably 4 pieces is much better than 2, and 10 pieces would probably be better than 4. It is calculus-y, and in fact, we'll find that in some cases, we're going to be able to, we can always end up writing this sum as an integral. In some cases, we can actually evaluate the integral. In other cases, we can write an integral but not evaluate it, going to infinitesimally small pieces. We can write it but not evaluate it, and then we're back to doing it numerically anyway. But in some cases, because there are integrals you can write down and they just don't have an algebraic solution. There just isn't an analytic solution to them, and we get some of those. However, there are certain cases where we actually can do it with calculus, and we're going to see that today. So let's now one of the places where it makes, one of the situations where it makes sense to use calculus is in a situation where there's a lot of symmetry to the situation. So here, for example, we have a charged rod that's been divided into 8 pieces, apparently. And we picked an observation location that's along what's called the midline. This is a line that's perpendicular to our rod, and we're assuming the rod's pretty thin here. So it's perpendicular to rod and goes through the middle of the rod. So we picked an observation location along this midline here. And that's obviously a pretty symmetric location because it's in the middle. Half the rod's on one side and half's on the other. And so that's a situation where we might hope to be able to get an analytical expression, which we'll eventually get to. But our first question is, if we pick this observation location here, A, along the midline, and this is a positively charged rod, so the charge of the rod is positive. What's the direction of the electric field at observation location A due to this particular piece 2? We have to do the pieces one at a time, and so the question is, if we just pick piece 2, what's the direction of the electric field at location A due to piece 2? All right, let's see what you said. So the popular vote is for direction 2, which is correct. So how did we get that? We, well, first we have to decide what the location of this putative point charge is, and it's surely going to be in the middle of piece 2. And then we just draw the vector r from the location of the charge to our observation location. And because this point charge is a positive charge, the electric field at that location is going to point in the direction of r. So we're going to have this delta E sub 2. So indeed, 2 is correct. So now the question is, Same observation location, but now let's look at piece 7, which is still, so what's the direction of the electric field at the observation location due to piece 7 of our rod? So you said direction 8, which is of course absolutely correct. So we find that drawing r vector r from the center of piece 7 to the observation location, this is going to contribute a delta E sub 7 in that direction. And now you can probably see that we found here that piece 2 contributed a field that had a plus x component. Piece 7 had contributed a field that had a minus x component. These pieces are equidistant from the observation location. So when we add them together, we're going to add delta E2 plus delta E sub 7. So we're going to move 2, put it at the tip of 7. So we get our resultant sum. So we see that the x components actually canceled out because we chose our observation location on the midline here. That's clearly not going to be true if we choose it over somewhere near the end. And so we should end up with an electric field when we add up all the pieces, and we have lots of pairs of pieces that are going to do this. So 2 and 7 were symmetric with each other. 4 and 5 are going to be, so in this case, all the x components will cancel, and we're just going to get a non-zero y component in this case. So we're almost ready to set this up and try to do it. One question though is we have to, so we know how to draw R, we know how to calculate the field of a point charge. The one remaining thing we have to think about is how much charge there is on one piece of the rod. Okay, now of course we could do it numerically. So if there's 4 nanocoulombs, so charge on one piece. I don't want it to be red. Okay, charge, it's still red. Okay, charge on one piece. I mean, if the total charge was plus 8 nanocoulombs and we have 8 pieces, so delta Q, charge on one piece, is 8 nanocoulombs divided by 8, which would be 1 nanocoulomb, right? But let's see if we can actually do that more algebraically so that we can use it in our derivation. So here's our question. If we have, in general, the rod's length is just L, and the charge of the rod is Q, and we've divided the rod into pieces whose length is delta X, which would be delta X is actually going to be the length of the rod divided by the number of the pieces, right? But in terms of this delta X, what is going to be the algebraic expression for the charge on one piece? let's see what you said. So some people say 1, most people said 1, some people say 2. How do we figure out which is correct? Now, hint, it's actually not 1. So let's see what we've got here. Suppose we have, so let's say the total charge is 4 nanocoulombs, and we have 8 pieces. The length is, say, 2 meters. And so we have 8 pieces. So delta x is 2 meters over 8 pieces, which is going to be 1/4 of a meter, right? So so if we have 8 pieces, the charge had better come out to Q over 8, which is going to be 4 nanocoulombs over 8, which is going to be 1/2 a nanocoulomb, right? So let's see what happens. If we have QL over delta X, we have 4 nanocoulombs times 2 meters divided by 1/4 of a meter, which is, we have an 8 on top, we've got a 1/4 on the bottom, so 4 times 8, that looks like it's 48 nanocoulombs, which is actually more than the total charge. So that can't be right. So let's try Q divided by L times delta X. 4 nanocoulombs divided by 2 meters times 1/4 of a meter. So we have 4 divided by 2 is 2 divided by 4 is 1/2 a nanocoulomb. So that's clearly right. And so there's 2 ways to think about this expression, which is important and will keep coming up again and again and again. One way is to think about this. Q over L is the charge per meter, the charge per unit length, so that it's 2 nanocoulombs per meter in that case. And then delta X is the length of one piece. So that's one way to think about it. The other way to think about it is that it's the total charge times the fraction of the length on one piece. So this is fraction of length, and that's total charge. Okay, so this is a key piece that's going to be coming together. And when we do that, so when we do this, we can pick any observation location and add things up and get it to work. So I'm going to show you the Python program here. So here is a VPython program that actually does this. The rod is oriented vertically here. And it does it in 3D. So it's picked a whole lot of observation locations. And this is a positively charged rod. We can tell that because the charges are red. We can see that there's some interesting patterns here. The electric field points away from the rod, which is fine. It seems to be kind of perpendicular to the rod until you get close to the end, and we've only sampled observation locations here, and then it's kind of pointing away from the ends. And we can see that if we change the number of pieces we're using here, so that used 40 pieces, but suppose we used 10 pieces instead, then we get a kind of a different prediction, okay? It's now not as uniform here in the middle because the charges are farther apart. And if we go to the sort of an absurd limit of making only 2 pieces, dividing the rod into only 2-point charges, we see that we get some pretty odd results, like the electric field in the center. So the point charges are here and here. The electric field in the center is very small. And okay, so that's a pretty bad approximation. But if we get up to 20 charges or so, 20-point charges, it starts looking pretty reasonable and uniform. Now, so next week in lab, you're going to write your own program to do this, but only at one observation location. But then you can move the observation locations around and actually see what's happening here. Okay, so what we want to do now is the more pieces you have, the more accurate the electric field is, yes, up to a point, after which in that program, the pattern of field you might have noticed between 20 pieces and 40 pieces, the pattern of field wasn't that different. And if we went to 100 pieces, it still wouldn't look that different, and the magnitudes wouldn't look that different. So there's a point at which, depending on how accurate you're trying to be, you've kind of got enough, and your changes are down in many decimal points down, and so it kind of doesn't matter. So up to a point, yes. Okay, so we're gonna see how if we can do this algebraically, and we're gonna do it with the orientation that the book uses, so that you can actually compare what we do in class to what's in the book here. So we're going to have a rod that's oriented vertically. Now this is a thin rod. It's not a big thick rod. So basically the idea is all the charges on the rod are kind of the same distance from whatever observation location we have. And we're going to pick an observation location somewhere on the midline here. Let's not use up quite so much real estate here. So we're going to pick it on one of these symmetric locations. And we want to get a general algebraic expression that depends on this distance from the rod to the midline here, this distance, which in our the way we've set it up is going to be x, but since the rod can be oriented more generally, we're going to end up calling it r. And so presumably it falls off with distance. But that's sort of the goal of this, is to find out how our electric field might fall off with distance. Now we saw that from those questions we did that we picked the symmetric location, and so so here's our observation location. So presumably the net field is going to end up only having a non-zero x component. In this case, the y components should cancel, but we can check that. So here's the procedure we use, and it's very general. So the procedure is divide your source into pieces. And then you want an algebraic expression for the contribution of one piece, so delta E of one piece. And there's a fair amount of most of the work we're going to do is going to be involved in setting this thing up. Then, so this is step 1, step 2, step 3, add up all delta E's, and for check the answer, and they're to make sure that we haven't made egregious errors and that the answer makes sense. So we're going to divide it up into pieces, and because in this case the number of pieces is going to vary. In fact, we're not going to specify right now exactly the number of pieces because we would like to be able to use calculus and make the number of pieces infinite. So what we're going to do is we pick a representative piece. So let's pick this piece up here. Now, in what sense is this piece representative? Well, it's not in the middle and it's not at the ends, both of which are kind of special cases. It's sort of in an ordinary location. And so presumably we're going to have a coordinate system where this is our x-axis and this is the y-axis, and we might as well put the origin at the center. And so therefore, the location of this piece is just going to be y, which is our variable, because we need to add up all the pieces. So all the y's are going to be different from the pieces, but every single piece will have the same charge. It's just y that's going to same size. And so the dimension of the piece is delta y. And the more pieces we have, the smaller delta y is. And so the location of this piece here, our standard piece, this location is going to be x is 0, y is y, and z is 0. And the location of our observation location is going to be x, y, x 0, 0, sorry. Now, we want our, so what variables do we want in our answer when we finally get all done? Well, we want x to be in our answer because then we can calculate the electric field along the midline for any distance from the rod. So answer, we want the variable x to be in the answer. We don't want y, because y is this thing that just tells us the location of a particular piece, and what we want to do is add up for all the different y's, and the variable y should actually go away. So y better not be there. Okay, so let's actually work this out for a particular piece. So the first thing we have to do is find the vector r. So here's our vector r that goes from the source to the observation location. And let's see, this is important, but I actually don't want it on this piece of what I'm doing right now, so I'm going to move it down here. Okay. So we need to write the vector r algebraically, so that's going to be well, it's going to be observation location minus source location, so it's going to be x 0, 0 minus 0, y 0, so that's going to give us an x negative y 0 for the vector r. And we're going to need the magnitude of r and then r hat, just like we did when we algebraically derived the field of a dipole. We're doing the same thing here. So the magnitude of r is going to be the square root of x squared plus y squared, negative y squared. And r hat is going to be r over magnitude of r, so x negative y0 divided by x squared plus y squared to the 1/2. And so now we can write this algebraic expression for the field of our special piece here. So we have delta E is equal to 1 over 4 pi epsilon 0. The amount of charge on one piece, we're going to call that delta Q for now, over the magnitude of r squared, so that's x squared plus y squared, times r hat, which is x negative y0 divided by x squared plus y squared to the 1/2. Now, we need to express delta Q in terms of our integration variable. Our integration variable is going to be y, because y is the thing that varies with the location of the piece. And so remember that what we just did for the horizontally oriented rod, we can use this general approach. So the amount of charge on one piece is equal to the charge over the length of the rod, and this rod creatively has a length L, times the length of one piece, right? And so that length of one piece here is just delta y. So the charge per meter times the length of one piece in meter. So we can rewrite this delta E is equal to 1 over 4 pi epsilon 0 Q, the total charge of the rod, divided by the length of the rod times delta y, times the vector x negative y0 divided by x squared plus y squared to the 3/2. We multiplied x squared plus y squared times the square root of x squared plus y squared to get that. So that's our expression for one piece. So now we have to add these things up. And at this point, we're going to find the x and y's. So do x, y, and z separately. Well, E sub z is to get, so E net is just going to be the sum of all these little delta E's. And so E net x is going to be the sum of all the delta E sub x's, etc. Now, we have the same symmetry that we had before, so here it's pretty clear that our delta E for this piece is going to be that way. But of course, there's going to be a piece down here, a symmetric location, that's going to give us a delta E. If this is piece 1, this is piece 2 in that direction. So the total field should add up to be in the x direction, and we can check that if we want to. So now we we can actually convert. So let's write these out separately. So we have delta E sub x is 1 over 4 pi epsilon 0 q over L. Delta y, we want the x component. So that's the x component of this vector comes down here, and we get an x in the numerator. And then we have our x squared plus y squared to the 3 halves. And delta E sub y is 1 over 4 pi epsilon 0 q over L delta y. And what we've got here is a negative y divided by x squared plus y squared to the 3 halves from that. Now we could just do this numerically. So I could give each of you a piece. We could divide it into 40 pieces, and everybody gets a piece. And you calculate these and add them up and report your answers, and we get that. But that would be for a specific location. And since we want an expression in terms of distance from the rod, we want to see if we can do this with calculus. So what we want to do is actually, let's move this so maybe we can still see the diagram if we're lucky. So let's take the x component. E sub x is going to be the integral of this delta x thing, except we have to write this now in terms of an infinitesimal piece size. So that what happens when we make this transition to infinitesimals is that this delta y here, which was the length of the piece, this delta y, just gets smaller and smaller and smaller, and that turns into a dy, an infinitesimal displacement in y. Now notice that this delta y didn't come from nowhere. We didn't stick it in there. It showed up. It came because the delta y came from the charge on one piece. Okay, that's where the length of the piece came into this integral. And so that's a really important physical quantity in this integral, this delta y, which turns into a dy. Our integration variable has real meaning here. So in the transition to calculus, we can write this as E sub x is going to be an integral, and here's what we're integrating, 1 over 4 pi epsilon 0 q over L x over x squared plus y squared to the 3 halves dy. So our delta y turned into this infinitesimal dy. But this is a definite integral because the rod is not infinitely long. So what are our integration limits going to be for this? Let's see if we can figure this out. So, okay, let's so what are integration limits going to be here? We want to So in order to answer this, you have to think about what the integration variable is and what values it's going to take on in this integral. Is there a VPython method for doing integrals? You have actually been doing integrals. You did integrals all last semester. You just didn't know what you were doing. Because what you were doing was, when you were predicting the motion of something, you said you calculated the change in momentum, which was F net delta t. And so that was a delta p, a change in momentum. You'd add it to the current momentum. And that gave you the new momentum. So you were actually doing an integral. Every time you went through that loop, you calculated another delta p and added it to p. And so p was essentially your numerically, it's called numerical integration. And that's what you were doing all last semester. Yep, that's right. You were doing integrals and you didn't know it all semester. Okay, let's see what you said here. So, okay, the most popular answer is 4. 4 is indeed correct. So let's see why. So we'll get rid of that. This is the right answer, and let's go back and look at our picture and see why. So y was the distance from the origin to our piece, right? So here's y. And so when we're at the origin, y is 0. Now, if the rod is total length L, that means the coordinate at the top of the rod, so y would have to be equal to L plus L over 2. And down here at the bottom of the rod, y would have to equal minus L over 2. And since y is the thing that's varying, it can only have values from negative L over 2 to positive L over 2. And so in fact, the right values for our integration limits are indeed negative L over 2 to L over 2. Now, another comment about, you're kind of surprised you were doing integrals all last semester. Another comment about numerical integration is that, in fact, most of the time it ends up being more generally useful than actually analytical integration the way we're doing right now, because you can do it under any circumstances. So if we want and we'll see that if we want to calculate the electric field at some observation location that's not on the midline, we're going to end up going back to doing it numerically. And what you'll do is you'll just calculate those delta E's and add them up numerically exactly the same way you were adding up delta P's last semester. But if we can do an integral with calculus, it's useful because it gives us a distance dependence. So now, and E sub y, of course, for completeness, E sub y is equal to the integral of 1 over 4 pi epsilon 0 q over L. What do we have here? We have a minus y over x squared plus y squared to the 3/2 dy from minus L over 2 to L over 2. And now you're going, oh boy, now I get to use its dy, because remember, y is our variable. The variable is what's varying here. X is some value here. That's the distance from the rod, but that's not changing. What's changing in our integral is the position of the pieces. So our delta y here is what turns into our dy. So again, this integration variable, this dy, has real physical meaning. It came from the length of one of our pieces. Now you're probably going, oh boy, now we get to do all that hard work and figure out how to evaluate the integral and all that stuff. But the bottom line is, we don't care how you evaluate the integral. You can look it up. You can ask Maple or Mathematica or Wolfram Alpha. You can use a symbolic integrator. My calculator will actually do integrals symbolically. It's a TI-89. So I don't care how you get from there to here. And it's not something you're ever going to be, this piece isn't something you're going to be asked to do on a test, unless it's a really simple integral, like the integral of x squared dx or something like that, which you should be able to do. But we evaluate by whatever method you happen to like. Well, it's d. Okay, so why is, okay, this is really important. So why is it dy instead of dx? Because the thing that was changing is the position of the piece that's contributing to the electric field. So we picked this little piece here that had a length delta y. And this y here, which is the coordinate of this piece, this is a variable, because if we picked a different piece, so suppose we picked this piece down here, y would have a different value, but the length of the piece would still be delta y. So the thing that changes when we're going to add all these pieces up, what's the thing that's changing? X is not changing. X is just the distance to the observation location on the midline. X, in this situation, X is a constant in a certain sense. At this moment, X is, it's really what you'd call a parameter. Okay, it's not exactly a constant, but it's definitely not the variable. It's, the variable is the thing that's changing. So what we're adding up is, and so this delta y, when we make our delta y, when we go to lots and lots and lots and lots of pieces, this delta y gets smaller and smaller and smaller and smaller until it becomes infinitesimal, and we just write it as dy. That's just a notation change to show that it's infinitesimal. Yes, absolutely. When you evaluate the integral, you're going to move all the constants outside. So to actually evaluate the integral, 1 over 4 pi epsilon 0, q and l are all constants. They're real constants. They would move outside the integral, and the integral you evaluate is the rest of that stuff. And what you get when you do all this is that the x component of the field at the observation location is 1 over 4 pi epsilon 0 q over L x times the quantity y over x squared times x squared plus y squared to the 1/2 evaluated from minus L over 2. So y evaluated from minus L over 2 to L over 2. And so what we end up is an E sub x equals 1 over 4 pi epsilon 0 q times over x times x squared plus y squared. Oh, sorry, x squared plus the quantity L over 2 squared to the 1/2, so the square root of that. So y, which was our variable, disappeared when we evaluated the definite integral, which is good. And when we evaluate this integral for y, e sub y, it in fact does come out to 0, which is satisfying. Now, since this rod can have any orientation, it kind of doesn't make sense to have the x in there, because we had the rod this way, and so E is that way. But we could easily have the rod that way, and E would be that way. So more general coordinates, we would actually write E sub r is equal to 1 over 4 pi epsilon 0 q divided by r. It came from evaluating the integral. The x squared in the denominator just came from evaluating the integral, and you can go do it yourself on whatever your tool of choice is. And so r squared plus the quantity L over 2 squared to the 1/2. This is where now this distance is this distance here is r. Now basically what we've done is gone to cylindrical coordinates, if you like cylindrical coordinates. Well, we do actually need math here. Now, so we can check some things. So how do we check to make sure this makes sense? Well, one thing is just to see if the units come out right. They should come out to newtons per coulomb, right? So we have Newton meters squared per coulomb squared. We have coulombs here. We have meters times the square root of meters squared, which is meters squared. And so that's the square root of meters squared. And so that looks like it's going to work, because the meters, we have meters, they cancel. Coulombs cancels one of these things, and we get newtons per coulomb. So if the answer's units don't come out to newtons per coulomb, we've got issues. Now, another check is a physical check. If you're far away, so here's our rod, it's 2 meters long or whatever, but now you walk across the street and across a football field and whatnot until the rod looks really, really small. In fact, to you, the rod looks like a point charge. So does it kind of come out to look like a point charge? Well, let's see if we can figure that out. So in our expression here, 1 over 4 pi epsilon 0 q r squared plus L over 2, the quantity squared to the 1/2. If we're very far away, that means that r is much, much bigger than L. So here we are with our approximations again. If r is much, much bigger than L, then this quantity is approximately equal to r squared to the 1/2. And so what we end up with is 1 over 4 pi epsilon 0 q over r times the square root of r squared, which indeed is 1 over 4 pi epsilon 0 q over r squared. Looks like a point charge. Yes, if the object was 3D, if it was a cube or a sphere, or in fact, the other thing we're going to talk about today really fast because we're running out of time is a ring, but I want to do it just so you can see this, and also so you can do the homework. I'm going to get a different equation. Now, there's a special case, and these special cases. So we said we wanted a distance dependence, but this is kind of a messy distance dependence here. But let's take a special case. So when we're far away, it looks like a point charge, okay? If we're very close, so it's the opposite case. So R is actually smaller than L. So we're really close to the rod. You're standing here looking up and down, like you're standing by a flagpole and you're looking up at it. Then we can make a slightly different approximation. So in this case, E sub x is going to be 1 over 4 pi epsilon 0. We have q times r squared plus L over 2 squared to the 1/2. In this case, if R is much less than L, then we can't get rid of this R. But in this sum, R squared is going to be a lot smaller than L over 2 squared. So this whole quantity is just going to approximately be L over 2 squared. And so when that gives us this approximation, we get 1 over 4 pi epsilon 0. We end up with a 2. I'm going to write it this way, Q over L over R. So if we're very close to the rod, then we have this, it looks like we have this 1 over R distance dependence. So E is proportional to 1 over R. So not 1 over R squared, not 1 over R cubed, but 1 over R if we're close to the rod. Okay, let me, because we are close to the end, I'm not going to work through the ring, which is worked through in great detail in the book. So, but I'd like to show you sort of geometric-graphically how this works. So what we're going to do here is we're going to do the same thing for, here's a uniformly charged ring. It's the red thing. And we're going to calculate the electric field due to this uniformly charged ring on the axis of the ring. So if I orient it this way, the axis of the ring is the x-axis here. Okay, but in general, we're just going to call it Z because it's cylindrical coordinates. So we're going to pick an observation location here, and we're going to pick our average piece here, representative piece. Note it's not on an axis. And this little magenta arrow is the delta E from that piece at the observation location. And then we're just going to march around adding up the delta E's. So we're going to move to another piece, and now we have 2 delta E's to add up. And now we move to another piece, and we've got another one. And so we're just going to march around the ring. Every time we draw R, we calculate delta E, we draw it here. So here are all the little delta E contributions of all these different pieces of the ring as we march around. And now we're back to where we started. And we can see that here are all the little delta E's we have to add up. And because of the symmetry of this situation, which is why we cleverly chose to do it on the axis of the ring, we are going to get an net electric field, and we add all these, the two of the components are going to cancel, even though we have this little 3D rosette of things, and we're going to get an electric field that just points along the axis of the ring. And now, if you're right in the center of the ring, you might think about what that should come out to be. Okay. And, oops, that wasn't what I meant to. Yes, what did I do here? What I want to do is share that. There we go. Okay, good. So for the ring, which is worked out in the textbook, and you can look at that derivation. So for the ring on axis, it turns out to be another situation where we can actually do this analytically. And a ring has some parameters. So the ring has a radius, and it's got a charge Q. And of course, our integration variable here is actually going to be theta, because we're going to have, as we step around the ring, we're stepping theta as we go around. So we're integrating with theta. And so by convention, again, because we're using cylindrical coordinates, we end up calling this the z-axis. So in cylindrical coordinates, you're in a system here. What you've got is if the origin's here, what you have is an r, you have an angle theta, and you have a z. So basically, we're going to call the axis z. And so what we end up with is, for the ring, E sub z on the axis ends up being equal to 1 over 4 pi epsilon 0 q times z over r squared plus z squared to the 3/2. And so on axis of the ring, and this actually is kind of an interesting distance dependence. Since the ring, the field has to change direction. So here, so it's got to point the other way there. So it needs to go to 0 at the center, which it actually does if z is 0. So that works. But actually, if we graph E sub z as a function of z, it's got to be 0 here. And so it actually has a maximum, which is kind of an interesting thing. And here it points the other way. So anyway, that's something that you're going to need for the homework, and we can actually talk about it a little more next Tuesday if you want to. Oh, yes. So do you need to memorize any of this stuff? No, you don't need to memorize the field of a ring. You don't need to memorize the field of a rod. You don't need to memorize the field of any other weird shaped thing we calculate. That will absolutely be given. You need to know the electric field of a point charge. And what you need to know is you need to know what these equations we've derived mean and how to use them. So you need to know what the symbols in them mean. Okay. And you also need to understand the procedure we used and to be able to do maybe one piece of it. Okay, so we'll practice with this a little bit this afternoon. And for attendance in chat, type what you think it's important for you to take away from this discussion. There are two things you have to memorize, exactly two. F equals QE, and E point equals 1/4 pi epsilon 0 Q over magnitude of R squared R hat. That is what you have to memorize. That's it.